So first of all, I should say that this is work that's been done in collaboration over quite a few years with a bunch of people. So let me single out my postdoc, Simone Bruggia-Paglia, and my student, Matthew King-Roskamp. I'll talk about some recent results with them. But also, this has been done in collaboration with Anders and his group in Cambridge. And let me also point out Vegard, who's in the audience somewhere, who's done a lot of work on this as well. And also, I want to just make a small plug. So Anders and I are finishing a book on compressive imaging. So I was told I could come here and give a talk as long as I plugged the book. So that's what I'm doing. So it should be done by the end of this year. So, OK. So this talk is going to be a little bit different, I think, to the other great talks that we've seen. I'd like to sort of go back and talk about compressive imaging. So the application of compressed sensing and sparse regularization ideas to imaging. And I want to focus on this term, the sort of what I've put, the unreasonable effectiveness. Why has this worked so well? How do we optimize it? And try and explain why this has proved to be such an effective tool. OK, so let me dive straight in. So here's 2006, and this is the famous Candace, Romberg, and Tau experiment done by Justin, who's somewhere in the corner. And this really launched the whole business of compressive imaging. So in this paper, what did they do? They took the Shep-Logan phantom. They sampled its Fourier transform along radial lines. Okay? So they were subsampling the Fourier transform. And then they compared reconstruction using TV minimization to classical recovery, so just zero-padded inverse Fourier transform. And what they showed is this exact recovery. Okay? And I think it's hard to overstate sort of the impact that this experiment had. It really showed people working in computational imaging that this is something that you could do and that this could have a dramatic effect on the recovered, or the quality of the recovered image. So of course, we all know the story since then. Compressed sensing for imaging has been a huge area of activity, starting with things like the single pixel camera by Rich Baranyuk and his group. And there's just been a huge amount of work in this direction, things like lensless imaging, various other optical imaging modalities. But I also want to highlight MRI. I think MRI has perhaps been the biggest success story for imaging applications of compressed sensing. So in 2017, there was FDA approval for compressed sensing type techniques. And then the big MRI equipment manufacturers now have commercial scanners which implement some type of compressed sensing ideas. Also, numerous other imaging applications, so CT, lots of optical imaging applications, seismic imaging, NMR, et cetera, et cetera, et cetera. I think it's probably hard to find an imaging modality where someone has at least not at least just tried to use compressed sensing type ideas. OK, so a little bit of theory. I think this theory will be familiar to virtually everyone in the audience, but let me just run through a couple of things quickly. So what's the standard compressed sensing setup? So the standard setup, we have measurements y equals ax plus e. X is the image, a is the measurement matrix, and e is noise. And our starting assumption is that X has a sparse representation. And just to keep things simple throughout this talk, I'm just going to assume that our sparsifying transform is unitary. Okay, so think a wavelet, orthonormal wavelet transform. I'm not going to look at TV or anything like that. That would be a slightly different story. So X has sparse coefficients, which will denote C throughout the talk. And typically, this will be wavelet coefficients. Then, what's the theoretical result? Well, if A phi has the restricted isometry property, and for instance, we solve quadratically constrained basis pursuit, so we penalize the L1 norm of the coefficients subject to fitting our data, then we all know that we have some guarantees on the stability of robustness of our recovery. So we recover X up to an error that depends on the best S-term approximation of its coefficients, so sigma SC divided by root S, plus eta, where eta is our noise bound. OK, so that's the first part of compressed sensing theory. The second part of compressed sensing theory is finding matrices that satisfy the RAP, or for which A phi satisfies the RAP. So of course, the nice theoretical construction are Gaussian random matrices. We all know very well that a Gaussian random matrix satisfies or has the property that A phi has the RIP for any unitary phi, provided the number of measurements m, so the number of rows in our matrix, scales like s times log n over s. Okay, and this is optimal for stable recovery. But of course, we know that Gaussian random matrices are not practical. This is not something we can implement generally for imaging. So then one starts to look at more practical matrices, for instance, subsampled unitary transforms or subsampled Fourier transforms, for instance. Again, of course, in a lot of imaging modalities, say MRI, for instance, Fourier measurements are what you get. Okay, so you're stuck with Fourier type measurements. So in this case, the situation is dramatically different. So the how we subsample and the condition that we get depends on where our sparsity is. So if you have canonical sparsity, so you have an image that is sparse itself, which happens in a small number of applications, then you know you're guaranteed the RIP if you have a number of measurements that looks like s times log cubed s log n. Maybe you can improve this log cubed to, well, you can improve this log cubed to log squared, but let's not worry about that. You have some polylogarithmic factor. How do you subsample in this case? Okay, you subsample uniformly at random. Okay, so you pick m frequencies from the uniform distribution. And then the situation changes if you have sparsity in wavelets. Okay? If your sparsity is in wavelets, which will be a typical imaging setup, then A phi will have the RIP if m is bigger than s times log cubed s log squared n. And how do you sample? So it's known that you should sample according to the inverse square law. Okay, so you draw your frequencies independently from a distribution where pi omega looks like 1 over omega squared. Okay, so at this point, so I've talked about imaging and talked about compressed sensing theory, and at some point, somehow it's tempting to just stop here. Okay, this gives you a description. We know with compressed sensing, if we want to recover an image, we have sparsity in wavelets or approximate sparsity in wavelets. This tells us how we should sample, and we're done. Okay. So I want to point out two reasons why this is not quite the full picture. So two paradoxes, and I think these are both somewhat well known, but not necessarily well understood. So first of all, the first paradox is that in practice, Fourier sampling outperforms Gaussian sampling. Okay. Even though these results on the previous slide would say the converse, okay, you have a better RIP condition for a Gaussian random matrix than you do for a subsampled Fourier transform. In practice, you always see better recovery with a subsampled Fourier transform. Okay, so here's a couple of just examples here. Okay, so that's the first paradox. Here's the second paradox. Suppose you're stuck with Fourier sampling. Okay, suppose you're working in MRI. How should you sample? Well, going back to the theory here, this says you should sample according to the inverse square law. So what happens if we do this? Here's the Peppers image. Here's power law sampling with this inverse square law. Okay, pretty bad reconstruction. And now we just increase the power. So I just increase it from 1 to 7 over 4, 5 over 2, and maybe change to a Gaussian, a truncated Gaussian distribution for drawing my samples. And we clearly see that we're actually getting better reconstructions here. Yeah.
Is this wavelet or Fourier?
This is wavelet sparsity, Fourier sampling wavelet sparsity. Yeah. So following on from that, the question is, what do people actually do in practice when they design sampling strategies, or what people use to draw their samples in practice? And it turns out that there's really not a consensus. So here's a paper, came out a couple of years ago, which is a review of the clinical literature on compressed sensing for MRI. And you probably can't see this table very well, but what this table does is it looks at various different works, and in this middle column here, they talk about the undersampling strategy that's used, the subsampling strategy. And essentially, everyone is doing something slightly different. Okay? Whether they're doing some sort of half-half scheme, then so half-half, you fully sample in some area, and then you randomly subsample elsewhere. So then you have to decide whether you choose a square, a circle, or a diamond, or something else. You could do half-half with variable density. You could do power law. You could do Gaussian. You could do generalized Gaussian. You could do things like Poisson disk sampling as well, et cetera, et cetera, et cetera. Everyone is essentially doing a different thing here. So, this is all in the context of Fourier sampling. But we have a similar story if we talk about binary sampling as well. Okay. So there are a bunch of imaging problems or imaging modalities where you really are stuck. Well, perhaps not stuck, but it's easiest to use binary measurements. So your measurement matrix A should have +1 or -1 entries. So in this case, the thing that mimics Gaussian random sampling is, of course, Bernoulli random sampling. But there's also, you can mimic the Fourier transform by looking at the Walsh transform. And you get a similar story here. So here's Bernoulli random sampling. This is theoretically optimal, but actually with Walsh sampling or Walsh-Hadamard, you get a much better reconstruction in practice. Again, you can prove that some kind of inverse square law sampling here is the thing that gives you a RIP, but actually in practice you can do better with some different type of sampling map, for instance, something like this. So, what's the remainder of the talk about? So the claim, so this gets back to this unreasonable effectiveness. The claim is that compressed sensing has been successful in MRI and imaging in general, not just because of sparsity and RIP and things like that, but because there's additional structure that is somehow exploited by the measurements that you're taking. So the reason I want to contend that the reason that compressed sensing has worked so beneficially for MRI is because you're naturally taking Fourier measurements. And these are actually better measurements to take than Gaussian random measurements. Okay, so this talk is going to be in two parts. So first of all, I'm going to talk about the design of sampling strategies for compressive imaging. And then I'm going to focus a little bit more on explaining these paradoxes. That'll be the second part. One remark. I'm going to just look at L1 type decoders here. For instance, basis pursuit or quadratically constrained basis pursuit or lasso and things like that. I'm not going to look at exotic structure promoting decoders, so I'm not going to think about tree models or anything like that. The reason is I think I want to stick with what is generally done in practice, and maybe this is slightly contentious, but I would say it's generally the L1 decoders that people use in practice. Okay. Are there any questions at this point? Okay, so let's move on to the first part. So in this first part, I'm going to talk about designing sampling strategies. So we need to specify our setup a little bit more. So I said I'm going to work with wavelets, so let's decide we're going to work with Dobeshi's wavelets. P is going to be the number of vanishing moments. And for reasons that will become clear in a couple of minutes, I'm also going to define the smoothness parameter corresponding to the wavelet. So this just determines the decay rate of the Fourier transform of the wavelet and the scaling function. Okay, so I said that my claim was that compressed sensing works well because there's additional structure that we're exploiting. So what's the structure that we're going to use? Well, I think you've all seen myself and Anders and others talk about this. We're going to focus on sparsity and level structure. Okay? So rather than looking at the total sparsity of my wavelet coefficients, I'm going to look at the sparsity within the wavelet scales. Okay? So at scale k, I'm going to let sk be the sparsity of my coefficients at that scale. Okay? So I divide my wavelet coefficients up into these dyadic scales and measure the sparsity within each one of them. Okay, and so just a bit of notation, then we can have then we'll define a vector S, which will be our vector of local sparsities. Why is this a reasonable thing to do? Well, you can demonstrate empirically via some tests that this is essentially the right kind of structure. That if you're using L1 type decoders, this is the structure that you're actually exploiting in the problem. No more, no less. Okay, so how should we sample? Okay, let's focus on the one-dimensional case. So suppose we're taking Fourier measurements. That'll be what we'll talk about for the majority of the talk. And suppose we're working in 1D. So we're working on one-dimensional images for the moment. Then what's the key property, okay, that should determine how to sample, that's going to tell us how to sample? And that's the frequency concentration of wavelets. Okay? So We all know that if I have a wavelet at scale k, I take its Fourier transform, it's essentially concentrated in a dyadic band in frequency space. So its frequencies, most of its frequency lies between 2 to the k and 2 to the k plus 1, okay, up to some constant. So this gives us a natural way to sample. If I have sk wavelet coefficients at scale k, and I want to recover them, then I should take mk samples from the corresponding band in frequency space, bk. And we're going to do that uniformly and randomly because, of course, random sampling is always a good thing to do in compressed sensing. So that's our sampling strategy. So we just go along to each of these bands and pick a number of samples depending on the sparsity. Then the question is, how many samples do we need precisely? And to avoid all the technical details, I'm just going to state the theorem like this. So this theorem says that the so-called RIP in levels, so the restrictive isometry property in levels, which is a sufficient condition for stable and robust recovery, this will hold provided our MK looks like this. Okay? So our MK needs to scale like the sparsity, SK, in the kth level. Then we get these off-diagonal terms. So we get these factors in, depending on the sparsities in the other wavelet scales. And the important point here is the coefficients here are exponentially decreasing in k minus L. Okay, so the influence of a scale that's far away is exponentially small. And this is not an unreasonable thing. Okay, so I've said that wavelets are concentrated in frequency, but they're not supported fully in BK, okay? Because the wavelets are compactly supported, they're Fourier transforms, therefore can't be. But they're exponentially concentrated in that region. Okay, so that's essentially how to sample in one dimension. Let's move on to 2 dimensions, or 3 dimensions, or just in general D dimensions. Okay, of course, we're really interested in 2D or 3D imaging. So how should we sample in this case? Well, the most obvious thing to do is to just take, rather than these 1D bands, just take 2-dimensional annuluses, 2-dimensional square annuluses, between 2 to the k and 2 to the k plus 1. And do exactly the same thing. Take MK measurements uniformly and randomly within this band, and then do some work through the theory, estimate the various quantities that you need to estimate, and you'll end up with a condition that looks something like this. So again, it looks rather similar to what we have in 1D. We have SK here, which is good, which is what we'd like to see. Then we have these 2 sums depending on the wavelet scales, the other wavelet scales. So this looks, okay, this looks somewhat reasonable. But there is a problem with this. And the problem with this is if you look at the first sum here, the exponent looks like 2q plus 2 minus d, where q is the smoothness of our wavelet. Okay. So this is a problem because for low-order wavelets, this term 2q plus 2 minus d might actually not be positive. If you take the Haar wavelet in 2 dimensions, so the Haar wavelet has q equals 0, okay, because its Fourier transform decays like 1 over omega, then, and d equals 2, then this term will be 0. So actually, if you look at the number of measurements you need in the highest frequency band, this is saying that it should scale like the total sparsity, okay, which is, of course, what we wanted to avoid. The whole point about this was to set up some sampling strategies that depend on local sparsities. So what can we do instead? So the idea is, so in this previous setting, we were taking frequency space and dividing it up into annular bands like this. And the idea is to do a more sophisticated division of frequency space. So rather than having just these bands, what we do is we divide it up into the tensor products of these 1-dimensional bands. Okay? So these become unions of rectangles. So we have something like this here. So if I take, for instance, the 3-3 region, then it's a union of 4 rectangles. And the rectangles have side length 2 to the k1 times 2 to the k2. So now we have more regions. Okay, so in 2D we would have, if we have R wavelet scales, we would have R squared of these regions. But that's really not a problem. We can just do the same type of thing. We say, let's take MK samples within this region. Okay. So K now is a multi-index. And we can go through and figure out the correct estimates. And you end up with a condition that looks something like this. Okay, so MK needs to look like some sum over the local sparsities with powers of 2 to the negative beta, where beta depends on K, so that's the region I'm in, L, the wavelet scale, and P and Q. Okay. And this beta is a known function. I could write it down. It's a little bit painful to write it down, so I haven't bothered. And part of the reason I haven't bothered is looking at beta itself doesn't really tell you very much about what's going on. So of course beta is a known function, so given the SLs, you could feed it into here and work out what your MK should be. That's fine. But it doesn't really give you much insight into the sampling that you end up with. So to gain a bit more insight, so we can do the following. So just to illustrate, this is the type of sampling pattern that you might end up with from the estimate on the previous slide here. So if you feed some typical SLs into this estimate, this is the type of sampling that you would end up doing, typically. Or you might end up doing something like this. This is the type of sampling that you would end up doing if you were just sampling uniformly within these dyadic bands. Okay. So how do we compare these two things? Well, what we can do, very simple idea, is just to look and count the number of samples that we take with this strategy within the dyadic bands, within the dyadic annuluses. Okay, so we count all the samples that we take in here. Okay. Let's call that number MK bar, for instance. So this B bar Ks are these dyadic annuluses. If you look at that number, okay, and so you take what you have in this estimate here, you sum up all the right-hand sides corresponding to the whole dyadic annulus that you're interested in, then you get a condition that looks like this. So MK bar needs to scale like SK times by the usual off-diagonal factors. And the point is now these are exactly the same as in one dimension. Okay. So this is the guarantee we had in one dimension. And what we're saying is that we can do this in D dimensions, have exactly the same measurement condition, but our sampling strategy shouldn't look like this. It needs to look something like this in order to do it. So in particular, we have to sample non-uniformly within these bands if we want to get these optimal guarantees. So just in terms of terminology, so this is what we would typically what we refer to as dyadic isotropic sampling. This is dyadic anisotropic sampling. Okay, so we need some kind of anisotropy to get the right kind of guarantees. Okay, so just to make a couple of remarks about this. So if you examine these guarantees a little bit more and you see the sampling patterns that they give rise to, then this is the situation typically if you have a very low order wavelet, you get a very anisotropic looking pattern. As you go to smoother and smoother wavelets, you get something that looks more anisotropic. Interestingly, you can also do this in the context of Walsh sampling. So if you're taking binary measurements, you have a similar setup, can devise similar kind of sampling patterns. And in this case, actually, this anisotropy persists regardless of the wavelet that you use. So actually, anisotropy is something, with binary sampling is something that you should generally, something that you would like to probably build into your sampling strategy. Okay, so how much time do I have? 20 minutes. 20 minutes, okay, plenty of time. Are there any questions?
Okay,
Yeah.
I'd like to ask a question.
Yeah.
Your model class for the images, that they have a certain number of wavelength coefficients, non-zero, a certain dyadic band. You don't assume anything about the energy of these decaying, because usually it's not only the number, but the
yes.
energy.
Yeah. So this, okay, so So the full theorem here, right, is going to say that, okay, so this is really, so this will assert that you have a rip in levels. And then this is, the rip in levels is going to assert some recovery up to some best, it's not going to be best S term error, it's going to be best bold S, because depending on the local sparsities now. So I'm not putting that in there because the statement is slightly complicated, but that's what's going on underneath. In the next part of my talk, I'm going to actually connect this to function classes. So maybe that might be what you're looking for.
Wouldn't it also be good to have sort of a universal strategy where you didn't have to know S? I mean, typically we develop a strategy, we don't need to know S, but it's sort of near optimal for every S.
So this is perhaps a point I'm going to make at the very end of my talk. The strategy is going to depend on the image. Okay? So and somehow this is natural. If I had an image with no fine scale details, I just take low frequency measurements. If I have an image with a lot of fine scale details, I need more high frequency measurements. So the optimal strategy is not going to be, it needs to depend on the image.
So you sort of feel you have a dictionary of images, or you have some images that will tell you what you should do.
That is actually something that we've done. Yeah.
Sorry.
So yeah.
Just jealous, okay. I see a Q in your formula, so I was just wondering, so that's the regularity of the Dobeshi. Now, if you put Meyer wavelet that can have infinite regularity,
So
what would be, the advantages or disadvantages?
So now I have to express my ignorance of areas of wavelets. So Meyer wavelets don't have compact support.
No.
Okay, so then that's a problem. I'm not sure how things would work in that case, whether they would. So yeah, so this is, although it only depends on P and Q, this only, well, so far we've only proven it for Dobeshi's wavelets. So yeah. Any other questions?
Struggling to understand the mathematical form of it because the second sum is over K.
That's a typo. Yeah, sorry, it should be over L equals K plus 1 to R. Yeah, okay, good point. Yeah, that's, okay, more awake than I was when I wrote the slides.
Just a quick question. And on that picture, you have basically a clear hyperbolic cross.
Yes.
But can you treat in this way hyperbolic wavelets? This is the tensor product of universal.
Oh, yeah, okay. So we never look at tensor products of wavelets. We do the normal thing, tensorize the MRA, right? So they're separable wavelets. But this, although we haven't done it, this sampling strategy would be the right one in that case, I think. So, but yeah. So, but yeah, we haven't done that. Okay, so let me move on to the next part of the talk, or the second part. So everything I presented up to now is really view this as a guide of how to design sampling strategies. And I'll get back to this point at the end of the talk. However, there's a bit of a gap, okay? These theorems do not actually resolve this paradox. They don't tell you that Fourier sampling will beat Gaussian random sampling. Okay? In fact, if you ask the question how many measurements will suffice, how many measurements in total, so I just sum up the MKs, take the sum over the everything on the right-hand side, I'm going to get total sparsity times a polylogarithmic factor. Okay? So this is going to be worse than the guarantee you have for recovery of sparse wavelet coefficients with Gaussian random samples. So this actually says we do worse. So how do we resolve this paradox? And I put this question to Simone about 2.5 years ago, and then we set Matt to working on it. And our idea was to try and take the results that we had and connect them with nonlinear approximation theory in wavelets, okay, and see what came out of that. So this is the setup that we settled on to do this. So we are going to work with 1D images, okay? And these are functions on 0, 1. Okay. So everything up to this point we were thinking about discrete images. Now we're going to think about functions so we can connect it to the approximation theory. And we're going to pick a function class, and I'm going to pick the class of piecewise Holder alpha functions. And then, then we're going to think about the wavelet approximation, nonlinear wavelet approximation in this class. Okay? So let's define sigma SF to be the best S-term wavelet approximation of this function. We'll continue using Dobischi's wavelets. Then there's a classical result that says that the sigma SF scales like S to the negative alpha. Okay. So the point is here, your best S-term approximation error, you don't see the discontinuities. You get a convergence rate that depends on the smoothness between the discontinuities. Okay, so that's best S-term approximation. How do we connect this with compressed sensing? So we're going to take this language that was comes from a paper of Ron and Albert Cohen and Wolfgang Dahmen, 2009. We're going to talk about encoders and decoders. So an encoder is for us, it's a linear mapping from L2 of 0, 1 to CM. So this just gives you your measurements. A decoder takes your measurements and gives you an approximation. So it gives you a function in L2. We're also going to be interested in a particular class of encoders that take Fourier measurements. So let's call those Fourier encoders. Okay, and so in this case, EMF is just a vector of samples of the Fourier transform of F. So then we're going to ask 3 questions. So first of all, is there an encoder-decoder pair that achieves an m to the negative alpha error over this class of functions? Second question, can I achieve this with a standard decoder? Okay, so for example, basis, pursuit, lasso, et cetera, I'm not interested in some construction or some existence proof of a decoder that doesn't actually lead to something I can implement easily. Thirdly, the practical question, can we do this with a Fourier encoder? So, first result. So first of all, just for means of comparison, suppose I use a Gaussian encoder, okay? And I use L1 minimization as my decoder. Okay? Then my error looks like m to the negative alpha, but I pay a logarithmic factor, which is log m to the alpha. Okay? And that's going to be crucial for what follows. So this is suboptimal by a factor of log m to the alpha. First theorem, there is an optimal encoder-decoder pair. So you can achieve m to the negative alpha. Okay? And moreover, you can achieve this by solving a basis pursuit problem of a size that's not particularly large, okay, or not unreasonably large. So that's the first result. Second result is about Fourier decoders. So there is a Fourier encoder-decoder pair that achieves m to the negative alpha rate up to a log factor where the exponent of the log factor can be arbitrarily close to 13 over 4. Again, this decoder, okay, we're using Dobeschi's wavelets throughout. It solves what is a weighted square root lasso problem. Okay, and there's some technical reasons for all that, but this is a weighted square root lasso problem. It's quite similar to the lasso, so it's not a big deviation from what one would call a standard decoder. So here's our theoretical answer to this paradox that I started with. So the point is that this log factor is bounded. It's independent of alpha, whereas in the Gaussian case, you have a log factor that's growing, or an exponent that's growing with alpha. So we've proved that this log factor is bounded. It is an open problem to improve the log factor of 13 over 4. We think we already have some improvements, but we know at least that it's a bounded log factor. Okay, so let me just make a few remarks about these theorems. So first remark, I want to say that these theorems are hiding nothing under the rug. We tried really hard to make this as clear as possible. So there are no discretization errors or truncation errors and that we need to estimate or anything like that. We're not making any unreasonable assumptions. We don't even need to know the norm of f or anything like that. Essentially, these theorems are essentially give you a black box. So you input m and alpha, so the number of measurements, your budget, the regularity alpha. It cranks the handle finds all the right parameters, the sampling strategy, and at the end gives you the approximation to f that achieves that error bound. In fact, this is the reason, so because these discretization and truncation errors, the reason we actually don't solve quadratically constrained basis pursuit, because then we need to know some kind of bound on our truncation errors. That's why we use this square root lasso. Yeah. Okay, so let me see. Let me talk about the proofs a little bit. So, thank you. So there are three key properties that make this possible. Yeah. And these are the following. So first of all, for this class of functions, most of the wavelets live at the coarse scales. Most of the large wavelet coefficients live at the coarse scales. Okay? And these coarse scales are saturated in the sense that at coarse scales, all the wavelet coefficients are large. On the other hand, at the fine scales, okay, I do need to capture the fine scales to get the right rate, but I have a small number of coefficients that I need to get. It's actually order log s. Okay? And this is crucial. So the idea is, we talk about the optimal strategy, is to do a very efficient sampling at the coarse scales, okay, where there's no sparsity, so we can do just classical sampling. In fact, for the optimal strategy, we could just sample the wavelet coefficients directly. Okay? And then at fine scales, this is now really the compressed sensing setting, because we have a small number of coefficients and we don't know where they are, because we don't know where the discontinuities are. So we can just do a Gaussian random sampling in that case. Okay. Then the point is okay, we have more measurements here, because, well, we have a log factor in our number of measurements here, but we don't actually need very many measurements because there aren't actually that many coefficients. So asymptotically, the number of measurements we need is actually equal to s plus little o of s. Okay, so it's asymptotic to s for large S. So that's how the optimal strategy works. Then the Fourier strategy is based on the same principle, but becomes horrendously complicated. And this is what took the time to work out. So we do a similar type of thing. We saturate the coarse scales. Okay? The fine scales are sparse. And then we have to play around with this estimate and do some funky things and balance various things to use this estimate. Okay? So we do a combination of fully sampling low Fourier frequencies, subsampling elsewhere, and play around with the various constants, and out at the end pops this 13/4 plus delta term. Okay, so let me move towards the end. So
does your strategy need to know alpha, or?
Yes, you need to know alpha.
Hidden in here? I don't see it.
Where is that hidden? Okay, so you need to know alpha to, P has to be bigger than alpha, right? The number of vanishing moments. Once you have P, that gives you Q, and then Q comes in there. Yeah, so, yeah, it's a good question. Okay, so let me move towards to summing up. So this talk has all been about sampling strategy design for compressive imaging. And so I thought I'd end on a rather more practical note and just give 4 recommendations, 4 take-home messages for how to sample in compressive imaging. Okay. So the first one is to fully sample the low frequencies. Okay. This is vital in all our proofs. It's vital to both the theorems that I showed. And this is really your insurance policy. You fully sample low frequencies, you're going to get something. Okay. Secondly, it makes a lot of sense to subsample outside of this region, do it in a nice, smoothly decreasing manner. So something like this. You have a region of full sampling here, and then you do a nice graded variable density outside that. The third point, so getting back to what Ron said earlier in the talk, your sampling strategy will depend on your image, the resolution, and the number of measurements. Okay? So it all depends on the local sparsities, and these are image dependent, and they're also dependent on your budget. If you have M measurements, then it makes more sense to just go for the coarse scale coefficients. If M is small, once M gets bigger, you can start picking up fine details as well. Then the final point, it gets back to this anisotropy, which was a surprise for us, but is important in practice, that your best sampling strategy might not be something radially symmetric like this, but it may be something like this, okay, especially in the Walsh case. Okay, just one final slide before I end. So this talk has in some sense been a reflection on compressive imaging, although the results are new. Let me just try and say one slide about where things are going next. So of course we've heard a lot about deep learning, and deep learning is the new thing in compressive imaging. However, there are issues with stability, which we've heard a number of times in talks so far. So I'd just like to point to a recent paper that we have on this, examining instability for neural networks. And there is a poster by Vegard over in the coffee room. So there is an open question. There is an open question that says, can we actually compute neural networks that have the same accuracy and stability guarantees of compressed sensing for imaging? Can we, and then further, can we actually find neural networks that in some sense provably do better? And there are some results. There's a poster by Matt looking at the first question as well. Okay, so that's it. All the theorems I presented are in this recent paper here. And then finally, just a shameless plug, I'm giving a whiteboard talk. And it's a rather different topic. So if you hated this talk, you won't hear any more of it. And if you like the talk, then second opportunity. Okay, thank you.